Probability. An event is an outcome from a random experiment. And probability is figuring out how likely that event will happen. And probability will always be between 0 and 1 because it's always a percentage between 0 and 100%. So you can't have the chances of something happening being 4 out of 3 or something like that. There's your sample space, which is looking at all the possible things that could happen. So if you're rolling a die, there's 6 possible numbers on the die, so your sample space would be all 6 of those. And an event is part of that sample space. So rolling a 1 would be an event of that sample space, and you have a 1 in 6 chance of getting that. I know that sounds pretty simplistic. It will get harder. You flip a coin, what are the possibilities you could get? Heads or tails. So the way that we write our sample space is we get to practice these extra fun squiggly brackets. And sometimes they'll turn out nice, and sometimes they'll just be massacred. So sample space of rolling a 6-sided die. Ooh, that one didn't turn out so good. So it lists all the possibilities. Sometimes if you have a bigger thing like rolling 2 sets of dice, sometimes a chart can help you make it nice because you can set up 1 through 6 on one side and 1 through 6 on the other, and then you can list all 36 possibilities. How many people have played the board game Settlers of Catan? Yeah. Love that game. It is a very fun game. So if you haven't played it, you should go out and play it. But on the game, like on the little circle things that have the numbers on them that you roll and you get your resources from there, you notice there's some dots underneath. Some have 1 dot, like the 2 has 1 dot. And that's supposed to tell you that it doesn't happen very often. Well, that is because out of the 36 rolls, the reason the 2 has 1 dot is there's only 1 2. There's only one way to get a 2. But if you look at the 8, which has 5 dots, sure enough, in here, the 8 happens 5 times. And in that game, if you're going to move the robber, you move the robber if you roll a 7, and the 7 happens the most times, but still only 6 out of 36 as far as its chances. Theoretical probability is based on the following calculations. So there's experimental probability where you just do an experiment, and theoretical probability of knowing what the chances are of getting something and then saying, well, my chances of rolling a 7 is going to be 6 out of 36. Because in our chart there was 6 7s and 36 total. But if you rolled a pair of dice 36 times, you're not guaranteed to get 7 exactly 6 times. Okay? So if you did an experiment, your experiment might be close to theoretical probability, but probably wouldn't be exactly theoretical probability. And the problem with experimental probability, like I'm going to do an experiment. I'm going to roll this dice. I got a 4. That means with this dice, I'm 100% sure that you will get a 4 when you roll it, because I just did an experiment and proved it. Well, the problem with only doing it once is you're not going to be close to theoretical probability. If you were to do it many, many times, you would get closer and closer and closer. So if you would like to, you can go home and roll a dice all night and see how close you can get to theoretical probabilities. Not recommended. I had a professor in university who wanted to find experimental probabilities, so he hired, I don't know how he got money to do this, but when you flip a tack, it can either land like that, so if you sit on it, it's painful, or it can land or it can land like this. It doesn't feel nice, but it isn't quite as painful. It's not 50-50, as you saw. It landed more one way than the other. So the only way to find out what this possibly could be theoretically is to do hundreds and hundreds and hundreds of experiments. And by doing those hundreds of experiments, eventually get closer and closer and closer. So he hired someone for a week, 8 hours a day. All they did was flip tacks and count them. And that person had a little bit of a mental breakdown, because you can imagine that you just go home and dream about flipping tacks and writing numbers. So there are certain jobs you don't want in life. Flipping tacks might be one of them. So you've got number of outcomes in which event A occurs and total number of outcomes in a sample space. And so if you were, like for example, like we said before, if you were to do it 36 times, you would expect to roll a 7 6 times. You would expect to roll a 2 only once. That would be your expectation. And we've got a little mini formula right here saying, from our chart before, I know that my probability of rolling a 7 was 1 out of 6. So if I were to roll a dice 100 times, 1/6 of 100 would be what I would expect to happen. Not guaranteed, but I would expect to get, what is that, 16.67 or something like that? That's what I would expect to happen. Of course, you can't get it 0.67 times. "20-sided dice, numbers 1 to 20. Has anyone ever seen a 20-sided dice? Event A is defined as the number obtained is a multiple of 4. What is the probability of A? How many multiples of 4 are there? Right, there'd be 4, 8, 12, 16, and 20. So when you're figuring out your probability of that event A, there are 5 events, and our total number is 20. So we've got a probability of 5 out of 20, which reduces to 1 out of 4. So if you rolled it 100 times, how many times would you expect to roll a multiple of 4? Well, our probability is 1/4. We do that 100 times, we would expect to get that happening 25 times. Same kind of question as if you wrote a multiple choice test of 100 questions and you guessed on each one of them, and you had 4 choices. Chances are you will still get 25 of them right. won't help you pass, but that's where, as math teachers, sometimes we mark exams and we're like, oh no, because there was 20 multiple choice on the exam. So even if you guessed, you should get 5 of them right, mathematically speaking. And sometimes you get students that get less than the 5 right. And you go, oh man. So you tried, and you did worse than guessing. So that's sometimes scary. Doesn't happen very often, but every once in a while, it does. And that's one of the, I was going to say that's one of the cool things, but it's not cool if you're failing worse than guessing. But we're going to figure out not only what are the chances, theoretically you should get 25, but we're going to be able to figure out what are the chances of getting 20? What are the chances of getting exactly 23? We can figure that out, and we're going to develop the mathematics that if we were to do an experiment, what are the chances of getting certain things? Like flipping a coin twice, what are the chances of getting heads once, is different than flipping a coin 8 times and getting heads 4 times. It's less likely to get heads 4 out of 8 times than it is to get heads 1 out of 2 times. So we're going to figure those kind of things out. It's going to be very neat. All right, sorry, I'm getting ahead of myself. Getting to the exciting math before we are there. Let's stay at experimental probability. So this is just how many times we count something over our total number of times that we've done the experiment. So we've got our little formula here, which makes sense. You flip a coin 8 times, you get heads all 8 times. Your experimental probability for heads is 8 out of 8. And that ratio is called the relative frequency of the event A. So we use that to estimate. We use that to estimate our theoretical probability. So for this one, our experimental probability says seven out of 10. So we did it 10 times and got heads 7 times. Theoretical probability would be 5 out of the 10 times, or 1/2. Unless your coin is like a weird shaped coin. Try this one. So based on the experiment, we would estimate that it would be 45 out of the 138. This, of course, can reduce if we wanted to 15 out of 46. Yes? And then if 350 cars pass and we feel confident in this number, we could say, well, it's going to be this fraction, 15 out of 46, because that's our probability. Out of the 350, when we multiply this, we get divided by 46 times 350, 114.1. So how can we explain that 0.1? Well, right at 11:59 and 59 seconds, a red car comes by the marker, and 0.1 of it gets across before it hits noon, and then you have to stop counting. So that would probably be most likely what would occur, right to the second. So of course here, putting our squiggle brackets and writing 114 is a better idea than putting the decimal place. And that also is to 3 sig figs, and it's an estimate anyways.